Hello everyone, all of you can hear me and I hope the presentation is visible to all of you. Okay, all right. So let's start today's discussion. Hello, yes, all right. If I'm not audible, please let me know. And if the presentation is not visible at any moment, please let me know. In case of any doubt, you may ask by raising your hand and then I will, uh, and then I will call your name and then you can ask your question. All right. So let's just start with today's discussion. So in the last session, uh, in the last Lavanya session, we discussed about similarity and equivalence of two matrices. Today's topic of discussions is slightly different from what we did in the last session. So in today's topic, we are going to study two new concepts. First concept is the affine subspaces and affine mapping, and the second concept is the inner product. All right. Uh, yeah. So let me start with an example. Okay. Example of a subset in R2. So we all know that a line is not a subspace until it passes through the origin. Okay, in R2, a line is not a subspace until it passes through the origin. So start with a line. Okay, so this is the equation of a line, and you can clearly see by the definition of this line that it is a subset of R2 first of all, because I'm taking a line in R2. And the second thing is that it is parallel to the y-axis. Okay, it is parallel to the y-axis. Now, is this line a subspace? That means, does it pass through origin?
No, sir.
No, sir.
No, right? So it's not a subspace. So it does not pass through origin. So it is a big no. No. Uh, right. So then what can we say? So, but it looks like a subspace because if I just, in some sense, get rid of this one, if I take this one out in some sense, then it is just a y-axis which is translated. Okay. So and y-axis we know it's a subspace. So it has the property of subspace in some sense, but it's not the subspace. Okay. So so what is this space? So this space, we can rewrite this space as this. All right. We can rewrite the equation as this. So let me just copy it from here, paste it over there. All right. So we have this equation. Yeah, this is the definition of the line. That we have given, which are drawn, which is parallel to in red on the xy plane. Now I can rewrite. I can think of this as translated version of the y-axis, which I was saying. So you can think that it is 1 plus 0. If I take 1 plus 0 vector out, then it is just the y-axis. And we know that this y-axis is a subspace of R2 because it passes through origin, and it's any two vectors. Sum of any two vector is in this line, and so on. So this is of form like this L can be written as a vector plus a subspace of R2. Okay, and what is a subspace? That subspace is nothing but the y-axis. Let's call that y-axis to L prime, and let's denote this 1 comma 0 vector by v. Now note that this 1 comma 0 vector, this vector lies in L. Okay, my original subset. This 1 comma 0 vector lies in my original subset. So you can rewrite this subset L a vector plus a subspace in R. Now, if I take any other vector in L, let's say 1 comma 2, all right. So 1 comma 2 is in L, and so that means if I take any other vector, let's say this 1 comma 2 vector or 1 comma 1 vector, so then I can again rewrite my L as 1 plus 1, 1 comma 1 plus L prime, where L prime remains the same, the y-axis, and the 1 comma 1 is the point. Just give me a second, guys. Yeah. Uh, so so this vector uh, this vector v is not unique because I can take any other vector in L to write down this expression to write it as a sum of a vector and a subspace. I can take 1 comma 1, I can take 1 comma 2, and so on. But this subspace remains the same because it is a shifted version of a subspace. So this subspace is unique. I cannot rewrite it as a some other subspace plus a vector. The vector is not unique, but the subspace is always unique. So in other words, I can take any I can take any vector of my L. I can take any vector of my L, let's say this vector, that vector, this vector, and take the sum of this vector with this subspace L, and I will get this shifted L prime line. Okay, L line. So I can take any vector in L, and I can express my L in terms of that vector and L. So this vector is not unique. I can take any vector from the subset, but this subspace is unique. Okay, so the subspace is unique, but not the vector. So what? So these subspaces, these subsets are called affine subspaces. Okay, they are not the subspace actually, but they are affine subspaces. You can they are like a parallel copy. They are shifted subspaces in your vector space. Okay, and the shift is given by or the translation is given by any vector in that subset. So in generality, you can say a vector V is, let's say V is a vector subspace, and a affine subspace of V is a subset L such that there exists a vector V in V, okay, and a vector subspace U in V such that L is equal to V plus U. That means or every vector in L is nothing but a sum of a vector V with some vector in. Okay, so that is the definition of this affine subspace. So the example that I started with, that was in R2, but in generality, uh, you can define affine subspaces in generality as well. You can take a subspace and you can take a vector and you can consider this, you can define this subspace and then this will correspond to some affine subspaces. Or if you start with any affine subspaces, then you will be able to find out a vector subspace and a vector V such that you can express your subset in terms of this. All right, it works both ways. Again, in generality, as I notice in this particular case, that this vector u is not unique. Similarly, in generality also, the vector u is not unique. You can take any vector uh, in L to express L as the sum of that vector and the subspace u. However, the subspace is always unique. Okay. Let's see some more example. So, uh, the affine subspaces are bigger classes than the subspaces of the vector space. Okay. So what do I mean by that? That means that every subspace of a vector space is an affine subspace. Okay. Any subspace is an affine subspace. So how do we see it? Uh, so in order to say that it's an affine subspace, let's say U is a subspace of V. So in order to say that U is a affine subspace, I need to express U as a vector in V plus a subspace. So what vector should I take? I can take any vector from U, or I can take zero vector. Zero vector is always in U. So um, so now take zero vector in U, and we have U as zero vector plus U. Okay. So there exists a vector U, there exists a vector zero, and the subspace U. So you will take the same subspace. So you can express it like this. So by definition of affine subspace, this is an affine subspace. Right?
So can you
In,
repeat, sir, from the definition that it is not unique from this, from the point?
yeah. So it is not unique. So for example, look at this example. You can take any other point to express, and then you will get the same subspace. You will get the same affine subspace. Okay, this is not unique. So what do I mean by that? For example, in this case, you can think that you can take any other vector, let's say this vector or this vector. You can take these any of the vector which lies on your subset, and then you add that vector to this subspace. You will get this translated one. Okay, you will always get that translated. So you can take any vector in your L. That is what it means. So keep this example in your head while thinking about a affine. So affine subspaces are nothing but a shift of a subspace or a translation of a subspace in your vector space. So in case of subspaces, you can take any vector from the subspace because subspace are closed under addition. So you can take any vector from the subspace. So in particular, if you take zero vector from the subspace, you can write u as a sum of 0 plus that subspace. So this is there, or you can just take any other vector also. So take any, or you take some v which is in u, and you can also express u as v plus u because ultimately uh, u is closed under addition. So you can take any vector and you are just adding that vector to u, and then it is closed. So you are still in u. You are not going outside. Okay, so this makes sense. Uh, yeah. So so in other words, any subspace of a vector space is an affine subspace. Okay. Now, if I take my vector space to be R2, then what are the possible affine subspaces? Okay. So a point is an affine subspace. That is clear. You can take any point because if you take a point, let's say you take x, y, then how to think of it as an affine subspace? You need to find out a point and a vector subspace. Now, what vector subspace will you take in this case? Zero subspace. Okay, zero, a singleton point zero. That will be your subspace. 0, 0. This is your subspace, zero dimensional subspace, and then your point will be that xy itself. Okay, so this can be written as this subspace. This point, any point, can be think of as point plus zero subspace. Hence, any point in R2 is a affine subspace. Similarly, any point in R3 is an affine subspace. The same argument goes with R3 as well. Okay. All right. Now, similarly, any line also is an affine subspace because if you take any line, what you can do, you can take that line, you can push that line to make it pass through origin. Okay. If you take any line in R2, you can push that line or you can translate that line to uh, to pass it through origin. So once that line passes through origin, you get the subspace. I'm giving this an intuitive picture in your head. So once you make it pass through the origin, you get a subspace. That will be your subspace. And what will be the vector? Any point in that line will be your vector. So any line is also okay. So for example, if you take y plus, for example, if you take y is equal to mx plus c type line, that means that equation of line in coordinate form it will be x comma mx plus c type. All right. Now you can think of it as, how can you think of this as? You can take 0 comma c out, and what is remaining is x comma mx. Now x comma x mx is a line that passes through origin. Okay, and 0 comma c is the point that you will take. Okay, so 0 comma c is a vector that you will take in the vector space, and x comma mx is the line that you pass. So in R2 also this is fine. All right. And now you can take whole R2 also. Why R2? Because R2 is a subspace of itself, and any subspace is a affine subspace. So affine subspaces are bigger classes than subspace. Not every affine subspace is a subspace. Okay. So for example, this is not a subspace. Any line is not a subspace because it does not pass through origin. So it is not a subspace, but it is a affine subspace. Okay. All right. Similarly, in R3 also, you can take any point, as I said, that will be an affine subspace. Any line will again be affine subspace by the same argument. Any plane will also be an affine subspace, and the whole R3 will again be affine subspace because it's a subspace. All right. So before I go into this fourth example, so let me give an example which is not an affine subspace. That is also
Sir, can you give an example of 3D line and 3D plane, sir?
yeah, you can think of it in the same way as you can think of it in this. You can think of the same in the R3 case as well. So let me, if you want, I can give you an example. So let's say this is example 6, or let's say this is 3.1. So consider this plane. Let's say consider this plane. All right. So now this is your R3. Now let's consider this plane. Okay. So this is a plane. Um, yeah. So just yeah. So this is you can think of it as plane. All right. Now it is a plane. So how to think of this plane? This is a plane which does not passes through origin. So this is not a subspace. Okay. But what is this plane? So this plane is parallel to xy plane. Okay. So let me write down this equation. So let me call this plane to be capital P. So what is capital P? Capital P is XYZ. Yeah, it is actually XY. Let's say some 2. Okay. And XY varies, X and Y vary in R. Okay. So clearly it is a parallel copy of the XY plane. And how can you express it as? You can again think of it as 0, 0, 2 plus the XY plane. Okay. So clearly this is a subspace and this is a vector. Okay. So this is also clear. Right, so this is an example of thing.
So just a silly doubt. Why do we put 0, 0, 2 here?
When did you join the meeting?
Just a few minutes ago, sir.
Okay, so what we do after the lecture, you can go back to the recording and then you can see the beginning of the lecture. Yeah, Jitin, do you have anything to ask?
Yes, sir. So you're getting rid of the twos because the two is not letting it be a subspace, right? So
You can
then,
think of it in that way. It's not getting rid of the thing, but yeah, you can think of it in that way.
okay.
I'm not getting rid of anything. I'm just, in order to prove that it is an affine subspace, I need to express my L as V plus U, some vector V in the vector space and a subspace U. Okay. So what is a subspace? That subspace is in particular the YZ plane, and that vector V is 0, 0. Now, what I said earlier, that this vector may come from any point in your, okay, it need not be just the
Okay.
1 point. It has infinitely many.
Understood. I got it a little bit, still didn't understand.
All right. So I was about to say something. Yes. Yeah. So what is not a affine subspace? Okay. So let's also think about that. So yeah, what is not an affine subspace? So consider this example. Let's take the R2 plane itself. So consider this example of this is a R2 plane, and now consider this uh, subset of R2, which is x comma x square. Okay. Now, how does this plane going? This space subset is going to look like. The subset is going to look like this, right? It will pass through origin. Yeah. So this is how it's going to look like. Yeah. This is how it's going to look like. All right. Now the question is it a affine subspace? That means,
Sir, is it a
Yeah.
subspace?
you tell me. But
But sir,
affine subspace, not all affine subspaces are subspace. You also need to keep that in. It is not a
So-
subspace, that is clear.
yeah.
But is it? But not every subspace, not every affine subspace is a subspace also. So is it a affine subspace?
No, sir.
Yeah. And why do you think so? Because I've written not over here. That's why.
No. Sir, actually,
Yeah.
sir,
So
Yeah.
X doesn't
not-
span all real numbers, right?
it can't
X
be
doesn't
obtained by
span all
shifting.
the-
It can't be obtained by shifting a subspace. Actually,
Right. Yeah. That is the correct way to think. It cannot be obtained by shifting of a subspace. Now, what are the subspace of R2? Subspace of R2 are the lines. Okay. And if you add a vector in a line, you must get a line back. You cannot get a curve, which you cannot get a subset which is curved in some sense. Okay. This is curved. Okay. It is not a straight line. It is a curved thing. So you will not be able to obtain this. So uh, what? So this is not a subspace because L cannot be obtained as vector plus a subspace uh, of R. Cannot be obtained as a vector and a subspace for V for some V for any V in R2 and U a subspace. So this is not a subspace. This is not an affine subspace. Okay. Yes, please.
So, like for R2, because only lines can be subspaces. So any
Lines
other
that passes through origin.
lines that passes through origin. So if we have any other shape, like any other curve, any other polynomial that is not in form of line, then that won't be a fine subspace.
Yes, because affine subspaces will be a translation of a subspace.
Yes.
So translation of a line must be a line. It cannot be
Yes.
some other form. Okay,
Yes, sir.
it cannot
Thank
be
you,
some
sir.
image of some polynomial. It cannot be that. So
Yes,
that
sir.
is the other. Yes.
Thank you, sir.
Okay. Good. Now this is the fourth example that I skipped earlier, but now let me go through it. So now you guys have already familiar with the solution space of a linear equation. Now the solution space of the linear equations are also the affine subspaces. Okay. How to see that? So suppose you have a system of linear equation like this, where where A is your some coefficient matrix corresponding to the system of equation. In particular, let's consider this example. Let's say you have the system of equation. Now the system of equation can be written as in terms of this matrix form. Okay. And you can quickly check that 1 comma minus 1 is a particular solution of this system of linear equation. Okay, you must all agree with that fact that 1 comma minus 1 is a particular solution of that. Now, how to write down the complete solution space of this? The complete solution space of this, to write down the complete solution space, we consider the null space of A. And how to take that? You can just take your vector B to be the zero vector. Okay. While doing so, and solve the system of equation, that means that is equivalent to finding out the null space of A. So you find out the null space of A which is going to be a subspace of R2 because your vector, because your xy, because you only have two variables, so your uh, so null space will be a subspace of R2, and your solution space will be nothing but the particular solution plus the null space. Okay. Any other solution will be just nothing but you take the particular solution and you sum it up with the null space. Now this is this is an example of an affine subspaces because there is a subspace here and then there is a vector here. So it is a translated version of the null space. That is your solution space. Yes, Sakshi.
Sir, here in the line, you're saying for the null space, it should be ax equals 0. Now, and then in the given example, it is 1 and 0. Can you please tell that?
Yeah, just read the line, just clause before this thing. Taking b equal to 0, 0. We get a null space. All right. You can always talk about a null space of matrix. Okay. So
Okay.
yeah. So what is happening in this case is, in particular, is that the solution space, you can think of the solution space as shifted version of a null space. Okay. That is what actually happens is. Okay. So solution space is nothing but a shifted version of a null space. Why can I say that? Because if you look at this column, if you think of this vector v, okay, the solution, the column vector v. This column vector v is nothing but this column vector v lies in the column space of A. Okay, you guys have seen this. B lies in the column space of C because with respect to the combination is given by the variables x1 up to xn. Okay, so B lies in the column space of A. Now, right. So we want to find out x1 up to xn, this solution set. All right. Now solving it for 0, which is again going to be in the column space of A for a particular solution of x, y, and 2n, we will get a particular solution. We will get a null space. And then any other solution to that will be a shift to that. Okay. So, yeah. So, for example, what you will do, you just apply, let's say, in this solution space, to consider a vector 1 comma minus 1. Now, in this case, what is the null space? In this case, the null space is 0 vector only. Okay. In this case, the null space is 0 vector. You can clearly see that. So null space is 0. So it is just 0, 0 vector. So this 1 comma minus 1 is the only solution in this case. All right. So it is a point that you are getting, and a point is a affine subspace that we know. Okay. In R2. But let's say you have a system where it has infinitely many solutions. That means the rank it's not the maximal rank. In this case, we are working with a square matrices. It need not to be the square matrix always. There can be some nullity also. So then you will get the solution space by taking the null subspace, adding that to a particular solution. So this is also an example of affine subspace. Yes, Anurag.
Sir, sir, if the null space is 0 vector only, then this solution of ax equal to b will be what we say will be shifted version of that 0 comma 0.
Yes.
If null space has infinite elements, like if it has infinite solutions, suppose, then
Yeah.
so what?
Let's say a line.
Yes. Then the ax equal to b will not have infinite solution, no, sir. So we can't say that.
Why?
We can't say that null space plus some vector.
No, why? No, just tell me that first. if null space does not have infinitely many solutions,
If
if null
does
space has infinitely many solutions, then why does it does not have infinitely many no solutions to this Ax equal to b? Any solution of this, any vector of this form is a solution to this system.
okay, then it will then the Ax equal to b, if we take non-zero, then also it will have infinite solutions.
Yeah, that is what
But
I'm
sir,
trying to say.
example you have taken 3x plus 2y is equal to 1. If you take
In this case, null space is zero. In this case, null space is zero. But you can have matrices with null space non-trivial.
okay. But so 3x plus 2y equal to 0 and x plus y equal to 0. This has
Yeah.
infinite solution. This has infinite solutions. Huh? This can have.
Does it?
Oh, 1 minute. Okay. No. Okay. So can you give an example where it has infinite solution and other also have infinite solution?
All right. So what I'm saying is the null space and a particular solution. Having a particular solution and a null space will give you the whole solution space. Now, why do I say that? I'm saying that because suppose you have a particular solution of a system of equation. You are working with a system of equation like this, and suppose x naught, which is a vector of this type, suppose x naught, which is a vector of a1 up to an, is a particular solution to the system of equation. Right. Then my claim is that for a vector v in the null space of A, v plus x naught is also a solution to Ax equal to b. All right. So how do we see that? That is what my claim is, right? Now, if you take, so instead of x bar, you need to take this vector itself. So let's take this vector. All right. Now, how do you multiply? This is how you multiply. Now, B lies in, now since B is in the null space of A, it means that AB is a zero vector. All right. So let's keep this thing aside. What we will get, then this is 0 plus AX naught. All right. Now, what is AX naught? Now, what is AX naught? AX naught is B,
B.
right? So that is 0 plus B, which is B. So what it means, what it says, this says that B plus X naught is also in the solution space of AX naught, AX equal to B. All right. And now since I've taken any B in the null space, what I get as a result, I get thus X naught plus null space of A is in the solution space of this. All right. So solution space is nothing but a shifted version of the null space and a point. And similarly, you can also argue if you take any point, if you take any solution, if you take any point from the solution space, now similarly, for now, let's say let W is in the solution space of Ax equal to B, then W minus X naught is in the null space. How? Because if you apply A over W minus X naught, what will you get? You will get AW minus AX naught. Now, AW is already in the solution space. X naught is the particular solution that I started with. So both are equal to B. So it is B minus B. So we'll get 0. So which implies that W minus X naught is in the null space of A. Right. Which further implies thus W is also of the form X plus null space of A. All right. Which implies that solution space of AX equal to B is equal to X naught is contained inside X naught plus null space of A. Now from equation 1 and equation 2, what you have proven is that both are equal. Now by 1 and 2, we have proven that solution set of AX equal to B is equal to X naught plus A and A. So I don't think so. I need to give anything more detailed proof than this, and everything is clear to you. Okay. So, so solution space. So it's the solution space of a system is nothing but a shifted version of a null space by a particular solution of the system. All right. So one example that we saw here. In this case, the null space is trivial. So we get only one solution, a point, which can be think of it as a affine subspace shifted of a origin. All right. So that is what the whole objective. You can similarly have an example where the nullity is non-trivial, and then you can have a shifted version of that. And by this, we have proved that solution space is always equal to a shifted version of a null space. All right. Now let's move on to the next topic of today's discussion, which is the affine mapping. So similarly, like in the case of the subspaces, vector spaces, you have a linear transform. In this case also, you have something which is called the affine mapping. So let's start with an example, so to make things easier. So consider this map. Okay. So this map is from R2, R3 to R2, which is defined as x plus y. XYZ maps to x plus y plus 1, comma z plus 3. Now, clearly, this is not a linear transformation. This is not a linear map. Okay. Can anyone tell me why?
Because on putting t0, it is not 0 comma 0. It is we are getting 1 comma 3.
Yes. So it is not a linear map. Okay. Linear map takes 0 vector to a 0 vector. Okay. So it's not a linear map. Now, but what kind of map is that? But it looks like linear. So if in somehow we can get rid of this vector, then it looks like a linear map, right? If I can get rid of the constant that I varied, then it looks like a linear map, right? Like in the case of the affine subspaces. In particular, if you can rewrite this map, yeah. In particular, if you can rewrite this map XYZ as 1 plus 3 plus x plus y comma z, then this other map, which is x plus y comma z, it is a linear map. Okay, it is a linear map T prime from R3 to R2. All right.
Excuse
So,
me, sir.
yeah.
Sorry to interrupt, sir. Sir, just one thing before move ahead. Is linear map is equivalent to affine map, or both these are completely different?
You tell me. I have not defined a affine map here.
Sorry, sir.
I have not defined a affine map here.
And nice, sir. There was a heading. I thought we are going affine
I have
map.
not defined it here. I'm starting with
Okay.
an example. Just wait for it.
Okay. Sir, my mistake. Sorry.
Okay, so so this map t x y z, I can think of it as a vector plus x plus y comma z. Okay, now this x plus y comma z, I can think of it as a image of some linear map because it is a linear map, right? X plus y comma z, it is a linear map. Okay, it is a linear map from R3 to R2. So I can think of T as a sum of vector plus a linear map. All right, where the linear map is defined like this. And now also notice that the 0, 0, 0, the vector 0, 0, 0 maps to 1, comma 3. Okay, as we noticed. All right, so 0, 0, 0 map to 1, comma 3. Now from both of these equation 1 and 2, what we can say? We can say that T of x, y, z is nothing but a vector which is expressed again in terms of T plus a linear map. Okay, such type of maps are called the linear affine maps between two affine subspaces. So affine maps are defined between two affine subspaces. Okay. Now, what are the domain and codomain in this case? In our case, the domain is R3, which is again an affine subspace of R3 itself, and the codomain is R2, which is which is again an affine subspace of itself. Okay, so it is a affine map between two maps. So such maps which are not linear map, but they appear to be a linear map, a shifted version of linear. You can think of it in that way also. So they are linear. Now we can motivate to our definition. What should be the definition of a affine mapping between two affine subspaces? So in some sense, it needs to have a linear map property. If you subtract some vector from the image, okay, if you subtract this thing from the image, then you are end up getting a linear map. So that should be part of the definition. And now what vector should I remove? What image of what vector should I remove? That should come from the affine subspace. Okay, so this vector I have used I can use this 0, 0, 0 to think R3 as a affine subspace of R3. Okay, I can think of R3 as a 0, 0, 0 vector plus R to think of it as an affine subspace. All right. So this image is nothing but for a fixed presentation of R3, this vector, the image of this vector. Okay, you need to remove this vector from this txy in order to get the linear map. That will be my definition of the affine. Okay. Yes, Jitin.
So T of 0, 0 is always going to be in the form of linear mapping, right? I mean, affine mapping.
T of 0, 0, 0 be always be in the.
Like, if you want to express affine mapping, you always have to get the transformation in terms of 0, 0, like the 0 vector, right?
Need not to be. Suppose in case of suppose you define a map from, let's say, in this case, I am defining from a vector space. It is also a vector space. So that's why I'm taking 0, 0, 0 vector. I can also take some other vector also. Let's say I can take 1, 1, 1. So not, yeah, I can take 1, 1, 1 also. And in that case also I can express it in, so then I will get some different linear map over here. I will not get the same linear,
Okay.
but it will be a linear.
Okay.
So this vector is not unique. Okay. As I mentioned earlier, this vector is not unique. You can have different vectors in the affine subspace presentation. This vector is not unique, but if you fix this vector, then you will get certain certain linear map.
Yeah, got it.
Right. Okay. So right. So now let's work with it. Now let's start the definition. Let me write down the definition. So let L and L prime be affine subspaces of V and W respectively. Let F be a function, just a function, okay, between these two affine subspaces. Now consider any vector V in L, the unique subspace U, and the unique subspace U such that L is of the form V plus U. Okay, in our case, V was 0, 0, 0, and U was the R3 itself, and my L was R3. Note that f of V is in L prime. Okay. Because why? Because V is a vector in L. So f of V will always be in L prime because it's a function from L to L prime. So hence L prime can be written as FV plus U prime, where U prime is a unique subspace of W according to L prime. All right. So then F is an affine mapping from L to L prime if the map G, which is defined as the subtraction. Okay, that is what I mentioned earlier. You need to subtract this thing. Okay, the image of this presentation, vector B and U plus B. What is U? U is the vector that you have taken from here. So it is U plus B minus this. All right. So this is what I did over here. So if you subtract then you will get a linear map. Okay, that is what you observe over here. If you subtract this vector from this vector, you will get a linear map. Because you can think of this vector as 0, 0, 0 plus x plus y plus, all right, and minus t of 0, 0, 0 is equal to t prime x y z. So their subtraction is equal to a linear. All right. So we need to fix. So while having this presentation, we need to fix this v u. Okay, we need to fix that. Yes, Anurag.
Sir, I've not understood this printed definition actually. This one I
What did you not understand? Can you be more specific?
No, sir. This all this got mixed up actually. I have become confused actually.
Did you understand this example?
Yeah.
Okay. So did you understood why I've taken this u? What is this vector
Yes,
0,
sir.
0, 0?
Yes,
Right.
this I have understood.
So that, yeah. So that is the same I am writing in the definition itself. So you have two subspaces L and L prime of V and W. All right. So in my example, I had R3. Yeah. I had R3 and R2. And I have a map. I had a map, which is T. All right. In this case, the map is given by F. I have the same map. Now R3 and R2 both are affine subspaces. Why? Yeah. Why R3 and R2 are affine subspaces?
So because they contain many affine
No.
subspaces.
No.
Because
Anyone?
So because we can write them in the addition of zero vector. I mean, yeah,
Yes.
zero vector. So we can say 0, 0 plus R3.
You
So
can
it
write with
becomes
any vector. If you take any vector from R3, you can express R3 because they are R3 is closed under addition, right? And you can just say that it is a subspace of R3. So any subspace is an affine subspace, right? So okay, so this is an affine subspace. And in particular, you can take zero vector also to write it down as 0 plus R3. Okay, and similarly, you can also think of it as, okay, now don't think of anything of this. All right, so that is what the second line says. Consider any vector v in L. So thus this v is in L. This is my L, this is my L prime, this is my F in the definition word. Now you consider any LV. So this is my V, and consider the unique subspace. This is the unique subspace U. All right, such that L is equal to V plus U. Okay, so L is equal to V plus U. That is clear. Now note that f of V is in L prime. Now what is f of V? F of V is T of V, which is in, what is T of V? So I defined this map as X plus Y plus 1, comma Z plus 3. Right. This was my T, X, Y, Z. All right. So what is T of V? Anyone?
1, 3.
Yes. What this was 1, 3. So now 1, 3 clearly belongs to L prime, which is R2. right? That's what this line say. Note that f of b is in L prime because it is a function from L to L prime, so it has to be in L prime. Now L prime. Now because L prime belongs to R2, sorry, because this vector belongs to R2, I can express R2 as sum of this vector. Why? Because it's an affine subspace. I can take any vector which is in the affine subspace to express that as the sum of that vector with a unique subspace. All right. So that is what I do. So I will take this vector. So I can do what I can express L prime, which is R2, to express R2, my domain. All right. Clear till this point? No problem. Now this subspace U prime will be again the unique subspace of W, which is clear because that is unique. The vector is not unique. Now then the affine mapping. What is affine mapping? Affine mapping from L to L prime. F is an affine mapping. The map T is an affine mapping. If there exists a function G, okay. So what you can do now, coming back to this function. Now, what can you do is you need to find out if G of U, sorry, if G of U is equal to F of U plus P. Okay. Now, in my case, G was T prime, which was defined like this. So how do we define T prime according to this definition? So X, Y, Z of T prime is equal to F of, that means T of X, Y, Z plus V. What is V? V is 0, 0, 0. All right. Minus F of V, which is T of V. Right. So what is this X, Y, Z? This was T of X, Y, Z. And this is 1, 3. And what we will get is X plus Y, Z. All right. Now this is when this is a linear map. So is this a linear map? Is this a linear map? T is 3 prime a linear map? T prime is a linear
Yes.
map?
Yes.
Yes.
Yeah.
So what does this mean? Does it mean T is a affine mapping? Yes. Okay. Right. So that is what I did in the previous exam. There is nothing fancy about it. All right. I hope this makes things much more clear because this definition is big. I can understand the confusion. I hope it's now more clear. You can, if it's not clear, you can again rewatch this part of the lecture once I upload, once you on the YouTube. All right. All right. So once this is done, and I have given an example of the affine mapping also on any subspaces, I think it is clear to all of you. Now we can move ahead with the topic of discussion, next topic of discussion, which is a dot product. This topic will be much more relaxed than the previous topics. All right. So I don't know how many of you are familiar with the dot product, concept of dot product, but it is part of a high school syllabus, not the high school, but the intermediate syllabus. So, but let me quickly recall what dot product is between two vectors in R2. Okay. So suppose you have two vectors in R2. So this is my R2 plane. This is the x-axis. This is the y-axis. Yeah, it looks like most of you are familiar with the thing. So suppose you have a xy plane, the R2 plane. You have drawn two vectors, v1 and v2. You have two vectors, v1 and v2. The dot product between them is defined as, suppose v1 is x1, y2. X2, v2 is x2, y2. The dot product is defined as x1, x2 plus y1, y2. Okay. Now, can you quickly tell me, in the given picture, what will be the dot product of these two vectors?
2.
2.
Yes, it is 2. The answer is 2. All right, good. So, given a vector in R2, you can always define a length to that vector. Now, how do we define the length? So, you can directly use this formula. Okay. Given a vector x comma y, you can define the length to be the x square plus y square and take the square root of the sum. All right. But how do we get this length? So the length comes from the definition of the dot product. Okay. So you take, so the length is nothing but, length of a vector is nothing but the square root of the dot product of the vector with itself. Okay. So you need to keep this definition in mind because we are going to generalize this in 10 minutes. Okay. So given a vector in R2, the norm of the vector, or the length, sorry, length of the vector is defined as the square root of the dot product of these two of the same vector. Okay. Now, if you take your vector to be x1, y1, and you take the dot product, what will you get? Let's solve this. So you will get x1 square plus y1 square, and then you are taking the dot product. So you are exactly getting the same quantity. Okay. So this is the length. Now, what is the length of v1 in this example?
Square root of 2.
Square root of 2. What about length of v2? No.
Square root of 5.
No,
Sorry,
it's not 5.
17. 17.
Yeah. Is it also 5? Is it 4 plus 5? It is 5. The square root of v1 is 5. The length of v1 is square root of 5. Okay, does everyone agree with this thing? This calculation? There is no doubt, I guess. All right. Now, so we have also seen, now given two vectors in R2, we can also define an angle between those two vectors. Okay. So usually the angle we measure is the anti-clockwise. That means starting from the x-axis and going towards the y-axis. That is the anti-clockwise direction. Okay? But we usually take the yeah, but we usually, in case of R2, or in case of R2, we usually take the shortest angle between these two vectors. So you can also have a possibility of a vector which is in this direction, let's say. Okay, so this is also one of the possibility of the vector. Then what will you do in this case? So what vector angle will you take? Will you take this angle by going the anti-clockwise, or by taking this angle going to the anti-clockwise? So we will take the shorter angle to find out the angle between. Okay. Right. So angle between two vectors are defined by this formula. What does this formula say? You take the dot product of the first two vectors and divide by their lengths, their individual length, multiplication of their individual length. All right. So what is the angle in this case? Can anyone tell me?
So what do you mean by the angle? Which angle is the angle between the two vectors?
Yes.
If the angle between the two vectors with the tails at one point.
Yeah, I've drawn a figure right next to it, right? In this
Theta,
figure,
yeah, theta will be the angle.
So is it 45 degrees?
you can calculate the value of theta,
Okay,
the cos in terms of cos inverse. So I want to know what is that cos inverse value inside the figure.
Cos
Yeah.
theta
Is theta
is 1 by
45
2.
degrees?
1 by
Cos theta
root
is
2.
1 by 2. 1
1
by
by
root 2. So it's 45
1
degrees.
by root 2.
That means it is 45 degrees, right? 5 by 4.
Sorry, earlier you were saying that anti-clockwise angle, no, something that we should take anti-clockwise or clockwise.
No, I'm saying the shortest angle.
If we take the positive of this cos theta, no?
There is no difference between them. Cos 180 minus theta is also cos theta.
Yeah. Okay.
Yeah, so what's the final answer? Pi by 4, right? Let's calculate
Pi
for
by
those who
4.
haven't calculated. Yeah. So it is the dot product is 6 divided by the norm is 4 plus 4. So it is 4 square root of 2 square root of 2 times 9, which is again 3. So we get, so this will get cancelled out. So it is 1 over root 2 cos inverse. theta.
45
So this
degrees.
is, yeah. All right, good. So now this concept of dot product can be generalized into a general vector space. Okay. Uh, so in particular, you can think of a dot product as a function with that a function applied on two vectors and gives you a real number, right? So similarly, you can define an inner product, which is a function on the product of Cartesian product of two vectors of the vector spaces and gives you the real number back. Okay, but this needs to satisfy certain properties. What are those properties it is satisfied? So first of all, the value, if you take the same vector, okay, if you calculate the norm of the same vector, that must be positive for all non-zero vectors in your vector space. And the norm, sorry, and the inner product of the same vector will only be equal to 0 if and only the vector itself is 0. Okay. So first of all, if you take the inner product of the same vector, it should be positive for all non-zero vectors. And if it is equal to 0, then the vector should be 0 itself. Okay. Now the second condition says the linearity. Okay. It is linear in the first coordinate. All right. It is linear in the first coordinate. Third property says it is symmetric. Okay. Third property said is symmetric. You can take inner product of V1, V2, or you can take V2 first and then V1 later. So the inner product remains same. So it is symmetric. Third property says, fourth property says it is linear. It is also fourth property also talks about the linearity. The second condition of the linearity. Okay, that means you can take the scalar out. Okay, if it is multiplied with the first coordinate, you can take the scalar out. By the symmetric property, by using the symmetric property, you can take the scalar out from the second coordinate also. Now, using the symmetric property, you can also prove that in the second coordinate also, this inner product is linear. Okay. So, in other words, inner product of two vectors is linear in both coordinates. Okay, and it is symmetric, and it is inner product of the same vector to itself is always positive unless the vector itself is 0. Okay, and it is 0 if and only the vector is 0. So these are the four conditions one need to remember, one need to prove to say a given function on a product of vector space, real valued function on a product of vector space is an inner product. All right. Yes. What's your doubt, Anurag?
So, like your first condition V dot V, sir, it is always positive because it is x1 square plus y1 square plus z1 square.
In R2, it is possible, but I'm not talking about R2 in this case. Look at this. This is vector space. Is every vector space R2?
No, sir, in
Yeah.
in Rn it is always true, na?
No, but I'm saying vector space V. Is every vector space is Rn?
So, can you give an example of other vector space other than Rn in which this first
Can
property is
anyone
not,
else give an example?
in which the first
Does
property is
anyone
not,
else?
in which the first property is not satisfied actually?
No. Can you repeat your question? Then it is not an inner product.
No. Can you give an example of that inner product defined on vector space where other than Rn, where the first property is not does not hold, sir, actually.
Then it is not an inner product. This is the definition of inner product.
Then it is not. So I, I want an example for this first condition, like where first condition is not getting satisfied. That is why it is being rejected uh, as not being inner product.
On Rn itself, you can define a different inner product where the first condition is not satisfied. Okay. So, for example, in R2 itself, uh, consider this R2 uh, with the inner product given as like this. Yeah. So, x1, x2, x1, y1, x2, y2, defined as yeah. So simplest what you can do is the simplest one is you can take your inner product to be defined to be just uh, R like this. Take any x1, take any vector v1, v2, and just map it to 0. The inner product is defined to be 0. So then it satisfies all three properties except the first one. That's the uh, yeah.
Excuse me, sir.
Just a second, Sakshi.
Sorry, sir.
Anurag, is it clear to you? Anurag? Are you
Yeah,
there?
so yes, so clear, sir. But can we some vector space other than Rn? Can we have that example on some vector space other than Rn?
You can take M2 cross 2 also.
Okay.
Define the same thing.
Okay, sir.
Yeah. Yeah. 。 All right. Yes, Sakshi, you had something.
Yes, sir. Sir, in the condition for inner product, there are some arrows, dot, comma, dot. Can you please define that? I've seen this first. I'm getting confused.
No, that's the symbol. This is the
That
symbol. This is a function symbol. Dot means you will have some vector over here. This dot means you will have another vector.
okay.
Yeah, it is a
And
symbol.
sir, the vector v comma v greater than 0, what are there are two brackets. That's also a symbol. Just
This is a function. It is defined like
in the
this.
first,
So
in the first condition, sir. In the first
yeah,
row.
yeah.
Yes.
So you
V.
take the first vector v here. Second vector is also v. That is what. This is how you're going to write it. Okay.
Okay.
All right.
Okay. Yes, sir.
Okay. So we have already we have already seen an example of inner product space. Okay. The dot product on R. Now let's check whether this dot product satisfy all these conditions to be qualified to say it as a inner product or not. All right. So can you guys quickly check all these properties? First property says that it is always positive. Now, what is it always positive? So my dot product is defined as v comma w is defined as v dot w. All right. So if you take what is v dot v, so v dot v is equal to 0. That means v is 0. That we already know from the dot product definition. All right. Similarly, v1 plus v2, v3. That means v1 plus v2 dot v3. So does it satisfy the linearity? It does satisfy the linearity. Okay. And similarly, the fourth condition and the third condition. It is also symmetric. Also, v dot v1 dot v2 is same as v2 dot v2, right? It doesn't change. Is it clear to everyone, right? There's nothing,
Yes, sir.
no doubt. Okay. All right. So dot product is an inner product space, is an inner product. And we say, let me add a line over here. Sorry. Moreover, we say a vector space V with an inner product is called an inner product space. Also, we denote V, we denote it by this. Sorry, we denote it by this. Okay. So R2 with dot product is an inner product space. Okay. So R2 with dot product is an inner product space. All right. Similarly, we can define our dot product on Rn also, as we discussed. So how do we define that? We can define it like this. You can take two vectors x1 to xn and y1 to yn and define their dot product to be the sum of the product of the coordinates. Okay, like this. You can check that this satisfy all those four properties. Okay, so it is an exercise to check. Dot product on Rn is an inner product. All right, inner product or not. So again, Rn with this dot product is also called the inner product space. All right. Now let's talk about inner product with that which is not as which is not same as the dot product. Okay. So let's take this example. Yeah, let's take this example. So first property is to check that v1 v inner product of v with itself is 0. All right. So let's check that. So let's take xy and xy. So xy minus xy minus xy plus xy plus 2xy. So what will you get? Xy is the answer. Right.
XY.
Now xy is 0 if and only if either x is 0 or y is 0. Yeah, but there can be a vector, for example, like this 1 comma 0. So let's take this vector 1 comma 0. Now, what is 1 comma 0? What is the inner product of 1 comma 0? It will be 0 because it is just xy, so it will be 0. But it does not satisfy. But xy, yeah. But 1 comma 0 is not equal to 0 vector. So it does not satisfy the first property, right? So this is not an inner product. All right, because it does not satisfy the first property itself. So we do not to check. We do not need to check other properties. Okay. Okay. Now, as in the case of R2, we had length of a vector. Okay. Similarly, in case of vector spaces, we have defined inner product for dot product. Similarly, we can define length as norm. So length generalizes to norm of a vector. Okay. So again, norm is a vector space. Norm on a vector space is a function that takes one vector and gives you a real number. Okay. And it is defined like this. So, and satisfy these following three conditions. First condition is that if you take the norm of the sum of two vectors, then it is smaller than or equal to norm of the uh, sum of the norm of the individual vectors, individual norm of the vectors. Okay, so this is also known as a triangle inequality, like thing. So what is a triangle inequality? That if you take the sum of uh, two sides of a triangle, it is small. It is always larger than the remaining side. Okay, the remaining side, the length of the remaining side. So this is like a generalization of that triangle inequality in the abstract setup. So yeah, because x plus y, when you have x plus y, let's say, so let's say you have this vector x, you have this vector y. Now what is x plus y? For x plus y, you need to form the, this is x, this is y. Now for x plus y, what you do, you consider, remember, recall this parallelogram law. So we draw this parallelogram, and then this is your x plus y, right? This diagonal is x plus y. But what is this line? This line is also x, y vector. So sum of these two vectors, so sum of length of this vector and length of this vector, sum of these two length is larger than the length of this vector, which is length of x plus y. So, so this is the triangle inequality. All right, this is what the triangle inequality is. Okay, makes sense. So first condition, a length or the norm should satisfy is the triangle inequality. Because in R2, when you have length associated with the dot product, it satisfies the triangle inequality. Okay, this is satisfied. If you take any two vectors in R2, then you can form this triangle, and then this triangle satisfies the triangle inequality. What it means that the norm of the third side uh, is smaller than the sum of individual sum of the length of the x and y vectors. Okay, that is what it means. So that is the generalization of the condition. So the norm, whatever norm we define on an arbitrary vector space, should also satisfy the triangle. Okay. Second condition is that if you take a scalar multiple of this, if you take a scalar multiple of a vector, so let's say you have a vector like this y, and you take a scalar multiple of this, some c times y, then the length also gets multiplied with that vector. Okay, and it should be independent of the sign of that scalar. Okay, whether you multiplied in the by a positive scalar or via negative scalar. Okay, so but the length is changed. So you just want to know the length, how much the length is changed. So just need to worry about the the quantity, not the sign of that. Okay, so it also satisfies this condition. The second condition is that if you multiply by a scalar of you multiply a scalar to a vector, then length of that vector changes. How much by how much vector, that vector should come out. All right, and that can be any real number. So this condition also be satisfied if you want to generalize the concept of length to any arbitrary vector space. The third condition is that if the length of a vector is positive or non-zero for all vector, yeah, the length of the vector should be positive or non-zero for all vectors, right? Length cannot be negative. So similarly, the norm cannot be negative of any vector. And if the length is zero, then the vector itself has to be zero. Similarly, if a norm of a vector is zero, then the length of the so if the norm of the vector is zero, then the vector itself should be zero. So these three conditions are sufficient to generalize the length of R2 to length of a vector in R2 to a norm of a vector to a norm of a vector in a vector space. All right. So now, first example that you will see is the length itself. Length on R2 defines a norm in on R2. Okay, so it is easy to check. We already know that it satisfies the triangle inequality, so that is checked. So what is the length? So let me just quickly recall. So we define length to be xy of this vector to be the x square plus y square. The first condition it's can be checked if you take x plus x1 plus y1. Sorry, if you take two vectors x1 y1 plus x2 y2 and you take their norm, then again by the uh, parallelogram drawing, you can quickly tell that this will be smaller than the individual norms, some of the individual norms. And the best part about this parallelogram is that you can generalize this argument to any Rn. Okay. So what you need to do, in order to generalize this, when you have two vectors, those two vectors, if they are independent, they will always span a plane. Just take that plane. Now that plane, think of that plane as R2, and then apply the parallelogram law. Then you can just generalize this triangular inequality to any two vectors in Rn. Okay. Okay, I will do that. So now what the second condition is that if you multiply
Excuse me.
C,
Excuse me, sir.
yeah, please go ahead.
Sorry to interrupt, sir. Sir, in the last condition, the mode, double mode x1 plus y1 plus x2 comma y2, how do we are gonna represent it in parallelogram? Sorry, maybe I miss it. I know the x1 comma y1 how to represent, but not this complete form.
How do you present x1 comma x1 comma y1?
Under root x1 square plus y1 square.
No, but in the triangle, so similarly you can do this with this also, right? This also, you just the sum of two vectors. You will get a vector after summing them.
Okay, sir, I will make it into one vector and then apply.
Yeah, that is how you are going to apply. But the proof comes from this fact by the parallelogram. That is what that is why I'm emphasizing on that. All right. The second condition is also you can clearly check. You can take the scalar out, and the third condition is also what that you can check for the length. Length is always positive in R2, that you guys know, and it is zero once only if the vector is zero. If only if the vector is zero. So I'm not going to complete this argument. Similarly, you can define a length of a vector in Rn. So how do you define? You can define in the similar fashion. Suppose you have x1 up to xn, a vector in Rn. So you can define the length of this vector as okay, like this. Now again, because it will satisfy all conditions, so I will let me give you a, you can other condition you can check, they are computational. The first condition is the triangle inequality condition. So let me give a proof of that. So again, suppose you have two vectors, x vector and y vector in Rn. Now, whenever you have two vectors, suppose what are the possibilities? Those two vectors can be dependent or they can be independent. Suppose they are independent. If they are dependent, then then it is trivial. Suppose if they are dependent, so that means y prime is some. So this is the first case. Y prime is some c times x prime. All right, or some some c in R. Then what is their sum? Their sum will be just x plus y, x c plus 1 x, right? And now you can just apply one of the condition. You can take c plus 1 out with the norm and in the brackets and then you will get this. So this is just this. The best part is that it will be just c times norm of this plus norm of x, which is same as norm of y plus norm of x. So you will get the equality in this case when they are dependent. Now the second case is when they are not dependent. Suppose x is not equal to cx for all c in R. That means they are not dependent. In that case, you have independent vectors, and whenever you have two independent vectors, you can span. You can consider the span. So their span is going to be so span of these two vectors y and x is going to be a plane in Rn. Okay, so it's going to be a plane in Rn. Now you take that plane. Okay, suppose this is your vector. This is x vector and this is your y vector. Yeah. And so you consider they are the plane that they span. Okay, so they will span some plane. So let's say this is the plane that is span. All right. So this is a plane that they span, plane P. Now this plane is You can think of it as R2, a copy of R2. And in this plane, you can apply the parallelogram law. You can consider their sum by taking the parallel copies, and then this will be their sum. So this will be their sum vector, the sum of the vector, because the sum of the vector will also lie in this plane because they are the span. So the sum will also lie in this plane. Okay. So mathematically, it's all making sense. Everything is coming into place, coming into the right place. So the sum will lie in this plane. So you can use parallelogram law to find out. And again, the norm is this vector. This is same as this. So norm of this is the same. A norm of this vector is x. So the norm will be this. So now you apply the triangle inequality and you will get the same result, that x vector plus this is smaller than or equal to. So in this case, it will be strictly smaller because the equality case you will get when they are dependent. Okay. So you prove this inequality. Right. So this is the proof of the triangle inequality. Other two properties you can just do. It is just computation, so I'm not doing that. Now you can, as I mentioned earlier, in the case of a length, I mentioned that you define length. How do you get this formula of length in terms of x square plus y square? You specifically take the same vector and apply it over and apply inner product over the same vector, and then you take the square root of that. That is how you get the length. And I mentioned then also, I will use this particular definition to generalize something for arbitrary spaces, and that is why I'm using here. So given an inner product space, V with an inner product, okay, given by this symbol, you can define a norm. How do you define a norm? So for let V is a vector in V, then you can define a norm like this. You take the square root of the inner product of the same vector with itself. Okay. Now, why is it defined? Why is it well defined? You can ask that. Because this quantity can be negative also. Can it be a negative quantity? Can this inner product of the same vector be a negative?
No, sir.
Yes. Why it cannot be?
Because it should be greater than 0 as per the condition of inner product space.
Yes. Yes. Exactly. So that is why that's the condition we are using here to define the norm. Okay. You need to. Yeah. This is an important point. Yeah. Good. Good. Okay. So this quantity is well defined. All right. So now you can also check. This defines all the properties of the inner product. Yeah. So first property, let me just do the first property. Other properties, I think, are computational, so you guys can do. They are direct from the definition of inner product. This will also be the direct. So instead of considering this, what I will do, I can take square both sides and I will do this. Okay, so this is fine, right? Now what is this? This is nothing but V. It is linear in both coordinates. All right. So we'll get V plus W, W, V plus W, and then V, VW, because in the second coordinate also it's linear. V, W. All right. Now we know yeah. Now these two things are the square. These are the, and we are adding this thing VW. Right. But this quantity, yes, yeah, it is not quite direct to prove this triangle inequality. Yeah. So what I will do, I will either update the node or I will discuss this triangle inequality part. But it is not part of your syllabus, so you can skip that part also. What I will do, I will add this in the notes while uploading. Okay, not today, but later I will upload it in notes. Okay, but this will follow the triangle inequality. It will satisfy the triangle inequality, so I'm skipping the proof as of now because there are few things that needs to be checked. Okay, but other properties, so I will write down check other conditions. Other conditions are direct for no. All right. First condition will also be satisfied. Maria, let's not go into details as of now. I will update in the notes. Okay, so here is an example of norm. Okay, so this norm is different than what we have seen till now. So we have seen that a norm can be defined on an inner product space. Norm can always be defined on an inner product space by this definition. Okay, but you can also have some other norms on your vector space. Okay, it need not to be coming from dot product unless it is mentioned. Okay, if so, in question, whatever question you will get in the exam, it will be either mentioned that this is the dot product we are using. This is the inner product that we are working with. All right. Now, let's take another example of a norm, uh, which we define on R3. Okay. So we need to prove that it is a norm. So first condition is the triangle inequality. So let's prove the triangle inequality itself. So this is the definition of the norm is the maximum of all these three quantities. So triangle inequality says, yeah. So triangle inequality says, yeah. So this should be smaller than equal to,
Excuse me, sir.
yeah.
Sir, just one, it might be silly question. Sir, why you are using the term triangle inequality? We are just simply working on the function and expression we are given.
Yeah, I gave an
Then
example, right? So for example, you can think of two vectors. Whenever you have two vectors, you can uh, you can obtain, how do you get the sum of the two vectors? You form a parallelogram, okay, and this parallelogram will correspond to a triangle. So it is a generalization of the first condition is nothing but a generalization of a triangle inequality. That's why I'm keep on calling it the triangle inequality.
and sir, just one thing. What does double mode represent? It's
Now,
the norm. Okay,
yeah,
okay. I forgot.
look at this definition now.
Okay, thank you, sir.
All right. So, um, yeah, the first condition. Uh, so let's take x1, y1, z1, x2, y2, z2. And then what is this? This is going to be maximum of x1 plus x2, y1 plus y2, z1 plus z2. All right. Now, what is the right hand side? Right hand side is the individual one. Now this is nothing but the maximum of x1, y1, z1. Similarly with this also, we will have some maximum of x2, y2, and z2. All right. So let's keep them aside and let's focus on this part. Okay. So suppose x1 plus x2 is the maximum. Okay. So you can assume that without loss of any generality, without loss of any generality, uh, assume that this maximum is x1 plus x2 is equal to x1 plus x2. Now, because it is sum of x1 plus x2, now on R1, we know uh, sum of two numbers are smaller than sum of their individual numbers. So this is always smaller than this. All right. Because x1 and x2, either of them can be negative also, right? But this thing will always be positive. So they are always either equal to or they are either larger than. Okay, so this is clear, right? Now we know that each one of this x1, this thing will be smaller than the maximum of the first maximum of this thing. Okay, so this will be smaller than the maximum, or this thing, the first quantity will be smaller than the x1, y1, z1 infinity no. The second quantity will also be smaller than the this thing. Smaller than or equal to. It can be smaller or equal to. So in other words, what we have proven is we have proven the first thing, which is the norm of v plus w is smaller than a norm of v plus norm of w. Okay. The other two condition I leave for you guys to work on this example and find out. So check other two conditions. Okay. Exercise. Only.
Sir,
Yeah.
sir, can you go to the last condition here? Okay. Sir, what is the use of writing infinite here? Understood the concept you are saying.
No, this is the definition. This is in the notation of the definition.
Oh, okay, sir. Actually, I don't watch the lecture. That's why. Sorry.
No, this is I'm defining now. It's not part of the lecture.
Yes, sir. I forgot. I have asked it before to this expression.
All right. No problem. So this is another example. This is another exercise for you guys to figure out. Okay. I'm not uh, discussing this. All right. Yeah. So in this case, you have uh, inner product defined like this. So this is the usual dot product, and there is some factor attached to c minus 5. Now the question is for what value of the c this inner product does not define it. This function does not define an inner product. Okay, that is the question. So, right. Yeah. All right. Okay, so we stop today's session at this point. Um, thank you all for being attentive. Hope to see you in the next session. Thank you.
Thank
Have a
you,
good
sir.
day.
Thank you, sir.
Thank you, sir.
Yeah, thanks.